Hello everyone, my name is Crosby. I am currently pursuing my Bachelor of Engineering degree in the field of Electrical and Electronics Engineering from Dr. Sivanthi Aitnar College of Engineering, Tiruchendur. And my teammates Akash Raj and Abhishek, who is pursuing his Bachelor of Engineering degree in the field of Electrical and Electronics Engineering from Sri Sivasubramanian Nadar College of Engineering, Chennai. We are here to provide a presentation about the topic which we are learned in this internship, and in the end we are going to demonstrate our internship project microwave oven. These are all the topics that we learned during the internship. On the first week, they gave the introduction to C, which is a basic programming language, and the conditional statements used in them like if-else statements, switch statements, etc. And similarly, loops used in them like for loops, while loops, and do while loops, etc. And we got to know various operators like arithmetic operators, logical operators, etc. And we got to know about the arrays and pointers and the implementation of arrays and pointers in different conditions, and the functions and strings and the storage classes. Basically, how the RAM and ROM differs and the basic storage elements in them. On the next week, we got to know about the embedded system and also the basics of microcontroller and microprocessor and the difference between them. And during the third week, we got to know about three new softwares like MPLAB IDE, XC8 compiler, PICSIMLAB. In our internship, we have used a microcontroller called PIC16F877A, which we have used in our project also. We got to know about various peripherals which is present in PIC16F877A. Before going into the project, we can see an overview about microprocessor, microcontroller and an embedded system. Microprocessor. This word comes from the combination of micro and processor. Microprocessor incorporates the functions of a computer's central processing unit on a single integrated circuit or at most a few integrated circuits. The microprocessor is a multi-purpose programmable device that accepts digital data as input, processes it according to instructions stored in its memory, and provides results as an output. Microprocessor operates on numbers and symbols represented in the binary number system. Internally, the microprocessor is made of three main units. The first one is arithmetic logic unit. It performs all arithmetic and logic operations in the microprocessor. Control unit. It is a subcomponent of central processing unit that manages the computer's operations. The control unit fetches instructions from the CPU's memory, represented in bits, and translates those instructions into control signals. Register arrays. An array of registers is used for holding data while it is being manipulated. Microcontroller. A microcontroller is a small computer on a single integrated circuit. A microcontroller contains one or more CPUs along with memory and programmable input-output peripherals. Microcontrollers are widely used in embedded systems such as home appliance, automotive systems, medical devices, and industrial control systems, etc. Microcontrollers are programmable, which means that they can be customized to perform specific tasks. The microcontroller chip is a high-speed device, yet it is slow when compared to a computer. Embedded system. An embedded system is a combination of computer, hardware, and software designed to perform a specific function. It may not interact directly with the environment. This is the basic structure of embedded system. The first component is sensor. It measures the physical quantity and converts it into an electrical signal which can be read by an observer or by an electronic instrument. The second one is AD converter. It converts the analog signal sent by a sensor into a digital signal. Processor and AICs. It processes the data to measure the output and store it in the memory. DA converter. It converts the digital data fed by the processor to analog data. Actuator. It compares the output given by the digital to analog converter to the actual output and stores the approved output. Coming into the project, our aim is to develop a model of microwave oven using PICSIMLAB. First of all, we can see that what is microwave oven. A microwave oven is an electrical oven that heats and cooks food by exposing it to electromagnetic radiation in the microwave frequency range. There are several modes in various microwave oven. Let us see about some of the modes as follows. Convection mode. It is simply used for grilling. In this mode, user can set the oven to preheat for a particular temperature. It takes 3 minutes to preheat the oven. After preheating is done, then the user can set time as per the requirements. Microwave mode. This mode is used to cook food in a traditional way. When you simply want to cook something like rice, Maggi, boiling potatoes, etc. So for cooking, microwave mode should be used where magnetron inside works and generates high frequency waves which cooks food from inside out. It uses a maximum power of 900 watts. In this mode, the maximum time that you set for cooking is 60 minutes. Grill mode. It is used for baking of cakes and cookies, etc. In this mode, heater turns on and fan is provided inside microwave chamber which circulates the air throughout the chamber to give that baking effect to the item placed inside. The requirements of this project can be explained by my teammate Akash.
Hi all, this is Akash Raj. I am from Assistant College of Engineering. I am here to continue your team presentation on the topic microwave oven. Let's get into the topics. These were the requirements needed for our project. First, we need to write the code for our project to implement in the PICSIMLAB. Where we are writing the code was, we are writing the code in the X8 compiler in MPLAB IDE. We are implementing this code in the PICSIMLAB in 16F877A microcontroller. In the microcontroller, we are using CLCD 16 cross 4 CLCD and the matrix keypad and the timer tube. Next, to get into the project demo, we need to just brush up our topics learned in the internship. First one is the interrupt. Interrupt is a process where an external device can get into the attention of the CPU. The interrupt will be considered to be an emergency signal in the microprocessor. It should respond to the interrupt immediately once it occurs. When the when the microprocessor receives an interrupt signal, it suspends the currently executing program and it jumps to an interrupt service routine to respond to the incoming interrupt. Interrupt service routine is nothing but where the interrupted code will be written. Each interrupt will most probably have its own ISR. Responding to an interrupt may be delayed or immediate depending on whether the interrupt is maskable or non-maskable and whether interrupts are being masked or not. There are two ways of redirecting this execution of the ISR depending on whether the interrupt is vector or not vector. When the interrupt occurs, the memory address stored by the program counter will be stacked and the interrupt will be executed. Once it's executed, the stacked memory address will be popped up and continues the execution. An interrupt vector is a pointer to where the ISR is stored in memory. All the interrupts are mapped into a memory area called interrupt vector table. Each interrupt source has two bits associated with it. One enables the interrupt and the other one checks whether the interrupt occurs or not. One common bit called GAE, that is Global Interrupt Enable. It can be used to disable or enable all the interrupts simultaneously. Global Interrupt Enable bit is very useful when writing a program because it allows for all the interrupts to be disabled for a particular period of time so that the execution of some important part of the program will be interrupted. Sorry, will it not be interrupted. Next, let's move on the topic interrupt service routine. Interrupt service routine is nothing but the code that is run when an interrupt occurs. It is a special function that only runs when there's an interrupt. The ISR should always clear the interrupt flag that triggered the interrupt. If it did not clear the interrupt flag, the interrupt will run continuously and it won't be stopped. So the interrupt flag should be clear once the interrupt was run. Then once the interrupt completed, then the program control will again reach to the execution of the program and the execution of program will be continued. On the interrupt, the CPU completes the current instruction and pushes the PC and onto the stack and clears the GAE to disable further interrupts. Next, let's move on to topic the internal block diagram of PIC 16 of 8778. This is the internal block diagram of the PIC. It consists of a program memory and the file registers and the RAM, ALU, and CPU and registers. In the PIC 16, 16 of 877A, we have a peripherals like input output ports, uh, timers, and ADC and all. Here we have a RAM with the four banks, each of 128 byte size. And we have the program EEPROM, which which is a 14 bits long, and a data EEPROM with 256 bytes. Let's move on to the topic, the peripheral features. I'm here. I'm going to explain the some of the peripheral features like I/O ports, ADC, and timer. First, I/O port. In the PIC 16 of 877A, we have five I/O ports. Each port have two control registers. One will be the TRIS-X and another one will be the PORT-X. TRIS-X, what will it do? It will set whether each pin is an input or output. When it was set to 0, it denotes it was set to output. When it was set to 1, it denotes it was an input. And the port X sets their output bit levels or their input bit levels. And next, ADC. ADC is nothing but it will convert the analog signal to digital. It is only available in 14-bit and 16-bit cores. The result of the ADC module will be 10-bit digital number. 10-bit digital number. From the 10-bit digital number, we came to know the exact value of the input analog voltage. The AD module has four registers, namely address fetch, address cell, AD 0, and AD 1. Next, timers. In PIC 16 of 877A, we have three timer modules, timer 0, timer 1, and timer 2. Timer 0 and timer 2 will be 8-bit timer, and timer 1 will be a 16-bit count timer with 8-bit rescaler, and it can be incremented during sleep via external clock. Timer will generate an interrupt on timer overflow. Uh, it can use the external pins as a clock in or clock outputs. Next, we move on to the matrix keypad. This matrix keypad, we are using it in our project. Uh, what we are using, the keypad consists of three columns and four rows. Whenever the user taps one button, column and the row corresponding to that button are shorted. How it was shorted? How was the shorted means these four rows are connected to the supply VCC through pull-up resistors, so that all the row inputs are typically 1 1 1 1 4 bits. If a user presses, let us say, if the user presses the button 6, when I feed the columns values by 0 1 1, the row output will be 1 1 1 1. When I feed it by 1 0 1, here this row will be 0 and this row will be 1. Again the row output will be 1 1 1 1. But when I feed it by 1 1 and 0, the button 6 will conduct the zero signal, because columns will be connected to the ground and the rows will be connected to the supply VCC. Thus, my rows output word will be 1, and this row will be connected to zero signal, and this row will be 1. Knowing that, I use the column 3 to conduct the zero signal via row 2, so that the controller came to know that I am pressing the button 6. This is how the matrix keypad will be work, and this column condition will be checked at every instance to know which button we are pressing. And next, we are going to see about CLCD. It is nothing but sorry, it is nothing but liquid crystal display. It is the mode of display used in digital equipment, replacing many other modes of display such as cathode ray tube, LED displays, and plasma displays. Often we are abbreviated the displays as LCD. This is a liquid crystal display. It's a thin flat panel which is made up of several blocks filled with liquid crystals. LCD works either by allowing the light to pass through it or by blocking it. Most of the LCDs used in the embedded system will be 16 class 2 and 20 class 4. Here we are using 16 class 4 display, because in PICSIMLAB the microcontroller 16 F877A will have a 16 class 4 display. This means the LED display can display, let us say example 16 class 2. 16 class 2 means 16 characters will be displayed into two lines. That is uh, 16 on one line and a 16 on another line. Here we are using 16 class 4 display, that is four lines, and each line will display 16 characters on it. And the input to this LCD will be, we can give it as a 8-bit or can be used as 4-bit. In this project, we are using as a 4-bit. Next, project demo will be continued by my friend Abhishek BS. Thank you.
Hi guys, this is Abhishek BS from SSN College of Engineering, Chennai. I am going to present my internship topic from Emertxe, given to me like microwave oven. Okay, let's start my project. Okay, I'm powering on the microwave oven right now. There are three modes: micro, grill, and convection, and there is a start button to start or stop the microwave oven. Okay, and now let's explore into the micro mode. When I press the micro mode, the power shows us 900 watts. Then let's set the time to some 55 seconds. 5, 5. And if we press hash to get enter and start to clear the number. Okay, we press hash. Okay, now the microwave oven started and it counts from 55 to 0. Um, okay, if you press the pause button like 5 means it gets passed, and if you press the button 6 means it stops, which will be illustrated right now. Okay. If you press the start button means the timer gets added to some 30 seconds. Okay. Next, let's explore into the grill mode. Let us set the time to some 22 seconds. And we press hash. Now the timer starts from 20. Okay. Now the door status is open. After closing it, the timer starts with the value where it stopped. Okay. 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Cooking time is up and the buzzer sounds. Okay, now let's go again to the menu panel and go press the button 3 to get into the convection mode. Okay, in convection mode, there is a preheating required. So let's set some temperature. Actually, the temperature range is within 250, but let us say we fix the temperature like 555, 555, and press hash. Okay, it shows invalid temperature. Oh, my microwave oven is functioning properly. Now let's fix some temperature, say 222, 2, 2, and 2, and press hash. Okay, the preheating time is some 180 seconds. Let's wait till that. Okay, within that meantime, let me explain how this system works. When we set some time using this keypad, which is at the bottom left, the timer gets preloaded with some value. Till the when the timer starts from some 60 seconds to 0, actually the internal timer inside the PIC16F877A IC gets loaded up. Say some value like 100 to some 101, 102, and it gradually increases on. Within that time, the timer which shows in the LED gets from some 55 seconds to 0. When it reaches the 0th second, the PIC16F877A is programmed in such a way that it shows that cooking time is up, and for indication of the same to the user, there is some buzzer which gets sounds up. Okay, now there's some 2 seconds, so sorry, 2 minutes left. Okay, I have coded this using the MPLAB IDE, which is exclusively for the microchip products and ICs, and I am simulating it using the PICSIMLAB. One minute left. Thirty seconds more. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The preheating is completed. Now let's set our time to some 10 seconds. 1, 0, and press hash. Okay, the timer now runs from 10 seconds to 0, and the product microwave oven turns off. That is returns to the main menu. Okay, cooking time is over.
On behalf of our team, I thank Emertxe for giving us a wonderful opportunity. Thank you.